Okay, so I'm going to review weak gravitational lensing acting on the microwave background. So this is a sort of precursor for the two talks that will follow. I thought I'd also just take this opportunity to update a little bit on the status of Planck. I should apologise right from the beginning that there's a very strong and binding confidentiality agreement within Planck, which basically means I can't show you anything that isn't in the public domain at the moment. All the plots I will show that have things on for Planck, they're based on simulated data, or they're based on public press release images. Okay, so let me just begin by saying a little bit about the future of CMB observations as I see them. So the first thing we want to do, and one of the main science goals of Planck, is to exhaust all the information in the primary, that is the temperature anisotropies, which are laid down at the time of recombination. And the reason for doing this is basically twofold. We learn a lot about the matter budget of our universe and the geometry, and we also learn, perhaps more interestingly, about the nature of the primordial physics that generate the primordial perturbations. So you can learn something about early universe physics. Another goal for Planck is to characterize much more fully the electric mode or E-mode polarization. So this is generated basically at two times, at the time of recombination or at the time of reionization. The large angular scales are basically sensitive to the signal from reionization, and by observing this we can learn something about the optical depth back to reionization, and perhaps a little bit about the actual reionization history of our universe. And then we get additional information from polarization about the nature of the primordial perturbations, which is nice and complementary to what you get from the temperature. Another big sort of goal in this area is to search for the imprint of gravitational waves in B-mode polarization, and this is another thing that we're hoping to do with Planck. But there's also a large number of dedicated ground or balloon-based surveys, which are specifically aiming for this survey, for this signal. So, for example, BICEP and SPIDER and other experiments. And then the sort of final thing in this field that's happening is trying to use the microwave background essentially as a backlight, either to light clusters, hence the Sanae-Zelvich effect, or to learn something about the sort of topology of reionization, or the matter distribution from weak gravitational lensing, all these secondary anisotropies, which require very high resolution experiments, such as the Atacama Cosmology Telescope, South Pole Telescope, AMI, and we can certainly do some of this with Planck as well. Okay, so Planck is a third generation CMB mission following on from COBE and WMAP, and its basic design goal is to measure the temperature anisotropies on scales greater than 5 arc minutes, basically to the fundamental limit. So to a limit where your noise is lower than cosmic variance. So you basically mine all of the cosmological information within the primary anisotropies. So Planck was launched just over a year ago with Herschel, and it's been routinely observing from the second Lagrange point since about August last year. It has 9 frequencies going from 30 gigahertz right up to 857 gigahertz. And the idea of having such wide frequency coverage is twofold. First of all, it allows you to subtract out astrophysical foregrounds and hence get at the CMB signal itself. But we can also do a lot of interesting galactic science by observing at these lower and higher frequencies. Planck's sort of best resolution is somewhat better than 5 arc minutes at these higher frequency channels, so that's about 3 times the best resolution of WMAP, and it has 20 times instantaneous sensitivity. So if you convert that into the sort of sensitivities that we'll actually have in the final maps, the sort of nominal Planck survey, and by nominal I mean based on 2 surveys, about 14 months of observation, is about 7 times the sensitivity that the final release of WMAP, that's the 9-year release, will have. Something that you may not be aware of is that recently Planck was approved actually to conduct 4 surveys rather than just the nominal 2 that it was originally planned to do. So it was launched with enough helium on board to complete 4 surveys. Obviously the improved integration time will improve error bars where we noise dominated. So Planck is at L2 in a Lissajous orbit, and it scans the sky basically by rotating about its spin axis at 1 revolution per minute, and the optic axis is at 85 degrees to the spin axis, tracing out large circles on the sky. And the spin axis is basically kept anti-solar to sort of minimize the thermal imbalances in the instrument. And then just slowly the spin axis just rotates around, keeping the sun anti-solar. So within about 6 months you cover the sky once. There's a small precession that's put on this as well, with a 6-month period, just to make sure that we cover these holes that would otherwise be present at the north and south galactic poles. If any of you are interested, there's a nice movie on YouTube by Chris North that actually shows Planck scanning, and this is what it's doing today. So it's scanning on this ring here, and in about a month's time, so this ring is expanding out this way, and in about a month's time we'll take our second look at the cold spot, which has been of considerable interest in us down here. So Planck has already covered the sky once. It's now on its second go, and it's about 70% complete on its second survey. So about the only data I can actually show you from Planck, and I'm sure many of you have seen this already, is this rather beautiful image that was released a couple of weeks ago. So this is based on the first survey data. It's a composite of all the frequency channels, and it's sort of designed to, the channels are weighted appropriately to exaggerate the beautiful galactic emission that you can see here, both synchrotron, these extended features, and dust in the plane. And there are some CMB features that are leaking through at high latitude here as well. So the basic sensitivity of Planck to the microwave background is shown in this plot. So the spectra we want to measure are this temperature power spectrum, the E-mode polarization power spectrum, its cross-correlation with the temperature, and hopefully the B-mode spectrum as well. And this B-mode spectrum has two components. There's a part on small scales from gravitational lensing, which has an amplitude that we're fairly confident about, because it's just set by the matter power spectrum. And then there's a component from gravitational waves, which dominates, which exists on large angular scales. And we don't know what the amplitude of this is. We don't have any good theoretical reason to assume it's as large as is allowed by the current constraints from the temperature. But if it were, the B-mode signal from gravitational waves would sort of be here, corresponding to a tensor to scalar ratio of 0.2. And Planck's sensitivities in temperature is the solid red line here. So this is the combining the 100, 143, and 217 GHz channels together. The power spectrum sensitivity, the noise power spectra is shown in solid for the temperature and for polarization in dashed red. So the point you should take from this, right, is that if you just compare these two lines up here, the temperature power spectrum measurement is going to be cosmic variance limited to L of about 2000. Whereas for polarization, comparing the dashed line to this line here, basically Planck is not really cosmic variance limited anywhere. It's just marginally cosmic variance limited around the certain peak regions. So in principle, there is scope for something beyond Planck to do a rather better job of the measurements of the E-mode polarization. Okay, just converting those noise spectra into power spectrum constraints, what we expect for Planck on the temperature power spectrum is sort of shown here. Again, I emphasize this is just simulated data, compared to where we currently are with WMAP 7 years and other experiments. So WMAP is cosmic variance limited to 500, so Planck won't do any better on these large scales, although arguably the control of foreground astrophysical foregrounds will be rather better, so the data is potentially more reliable on these scales. But the real advantage is through the rest of the acoustic peaks and down into the damping tail, where Planck will do a much better job and be cosmic variance limited basically all the way out to about here. So this enables you to do lots of interesting science in terms of cosmological parameters. The only one I'll highlight here is constraints on the tilt of the primordial power spectrum. This is certainly the thing that we get asked most about by sort of early universe cosmologists. And all I'm going to say is that if the sort of central value in W map retained stays where it is, then Planck ought to get about an 8 sigma detection of tilde. In practice, doing this is actually quite difficult well out into the damping tail, because there's all sorts of issues that become important, like uncertainties in your experimental beam, theoretical systematics. As well as working on lensing, Chris Herat has been doing a wonderful job sort of recomputing the recombination history, which turns out to be rather important for parameters in this part of the spectrum. And then, of course, the issue of point sources, which dominate on small scales.